Euclid Maths, Euclid Maths, Euclid Maths.
Welcome to part 3 of our series of lectures on vector differentiation. In this lecture we are going to learn the gradient of a scalar field and its properties. The applications of gradient operator will be discussed in the next part. Without further ado, let's dive in.
Consider a function f from R2 to the real line R. This is a scalar field defined on the two-dimensional space R square. Now, we have already seen that such a function has two partial derivatives, dou by dou x and dou by dou y. We use those two partial derivatives to define the gradient of this particular scalar field. The gradient of this function is defined by grad f or del f equals I cap dou by dou x plus j cap dou by dou y. Here I cap is a unit vector ordered by 1, 0 and j cap is the unit vector in the y direction 0, 1. Here del f or grad f is the symbol used to denote the gradient of this function f of x, y. Actually, z is equal to f of x, y represents a surface. For this surface, we find the gradient. Del symbol is also called nabla. So, we can read it as gradient of f or del f or nabla f. Now, let us consider the next case, a function from R3 to the real line R. This function is a scalar point function defined on the three-dimensional Euclidean space R3. We know this function has three partial derivatives, dou by dou x, dou by dou y and dou by dou z. So its gradient is defined by gradient of f or grad f or del f equals I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z. Here we can observe one fact. Here the function is a scalar point function, but the gradient is a vector point function. We must remember one point. The gradient of a scalar point function is always a vector field. So, if I want to call del f a vector field, I have to assign a magnitude and a direction to del f. Then only I can call it a vector. So, what is its direction? What is the magnitude of del f? Let us see. Actually, if we take a function f from R3 to R, now del f is always perpendicular to the given surface f of x, y, z equals a constant. This equation f of x, y, z equals c represents a level surface and del f is always perpendicular to this level surface. In other words, we can say del f is a normal to the surface f of x, y, z equals c. Now, what is the magnitude of this del f? The magnitude of del f can be interpreted in two ways. But let us restrict ourselves to this formula only. The magnitude of del f is given by the formula norm del f equals square root upon dou f by dou x whole square plus dou f by dou y whole square plus dou f by dou z whole square. So I assigned a magnitude and a direction to the gradient. So one point is clear. The gradient of a scalar point function is always a vector field. Let's see a few examples. As a first example, let's consider a scalar point function on R cube given by the formula f of x comma y comma z equals xy plus yz plus zx. If we want to find out the gradient of this function, we have to first find out dou f by dou x, dou f by dou y and dou f by dou z. Dou f by dou x for this function equals y plus z. Dou f by dou y equals x plus z and dou f by dou z equals x plus y. Now the gradient of this function is gradient of f or del f equals I cap y plus z plus j cap x plus z plus k cap x plus y. So this gives the gradient of the given scalar point function. Our second example is g of x comma y comma z equals xyz plus y square. For this function g of x comma y comma z equals xyz plus y square, if we find out the partial derivatives dou g by dou x, dou g by dou y and dou g by dou z, we get dou g by dou x equals yz, dou g by dou y equals xz plus 2y, dou g by dou z equals xy. Now what is the gradient of this particular scalar field g? It is del g. Del g equals I cap dou g by dou x plus j cap dou g by dou y plus k cap dou g by dou z. Now we have to just plug in our values of partial derivatives here. Then we get del g equals I cap yz plus j cap xz plus 2y plus k cap xy. As a third example, let us take a scalar point function defined on R3 as u of x comma y comma z equals x sin y minus z cube. For this function, dou u by dou x equals sin y, dou u by dou y equals x cos y, dou u by dou z equals minus 3z square. If we want to find out del u, the gradient of this u, we get grad u equals I cap dou u by dou x plus j cap dou u by dou y plus k cap dou u by dou z. Now substitute the partial derivatives of u here in this formula. Then we get gradient of u equals I cap sin y plus j cap x cos y plus k cap times minus 3z square. Now we require total derivative formula to use it in our further work. Here let us consider a scalar point function f defined on R3. So here f is a function from R3 to the real line R. Now let us take this formula df equals dou f by dou x dx plus dou f by dou y dy plus dou f by dou z dz. This is called total derivative of f. Now let us derive a small formula here. First, let us consider a vector r cap equals I cap x plus j cap y plus k cap z. This vector is called a position vector. Sometimes it is also called velocity vector. Now, if I find out dr cap, we get I cap dx plus j cap dy plus k cap dz. This denotes the tangent at that point xyz. So, dr cap is a tangent vector at that point xyz. Now, let us take the dot product between the gradient of f and this dr cap. If del f is dotted with dr cap, let's see what happens. Del f dot dr cap equals I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z, dotted with I cap dx plus j cap dy plus k cap dz. If we perform this dot product, we get dou by dou x dx plus dou by dou y dy plus dou by dou z dz, which is nothing but df. So, if we take the dot product between these two vectors del f and dr cap, then the result is df. So, df equals del f dot dr cap, which is a very important formula which is to be used in the further work. Let's understand the direction of the vector del f in detail. Here, let's consider a scalar point function f defined on R3, the three-dimensional space. Let us suppose that w equals f of x comma y comma z. Consider a level surface f of x comma y comma z equals c. Here c is a constant. Now, because f is a constant, its total derivative df is 0. Because f of x comma y comma z equals c, df becomes 0. What is df? We derived one formula for df. Del f dot dr cap equals df. Because df is 0, del f dot dr cap becomes 0. If the dot product between two vectors is 0, what we can say about them? Those two vectors are orthogonal to each other. Here, del f and dr cap are orthogonal to each other because their dot product is 0. Dr cap represents the tangent vector, so del f represents a normal vector. So del f is always perpendicular to the given surface. The gradient of a scalar field satisfies a few properties. This gradient of a scalar field behaves like a derivative of a function of single variable. If we take two scalar point functions f and g, we can observe the following properties of the gradient. The first property is del of f plus g equals del f plus del g. The second property is del of cf equals c times del f, where c is a constant. The third property is del of fg equals f del g plus g del f. The last property is del of f by g equals g del f minus f del g upon g square. These properties are very easy to prove. These properties depend on the properties of the partial derivatives dou by dou x, dou by dou y and dou by dou g. So, for example, if we want to prove del of f plus g, what is del of f plus g? I cap dou by dou x of f plus g plus j cap dou by dou y of f plus g plus k cap dou by dou z of f plus g. It can be written as I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z plus I cap dou g by dou x plus j cap dou g by dou y plus k cap dou g by dou z. It in turn becomes del f plus del g. So we can prove del of f plus g equals del f plus del g. Similarly, we can prove the remaining properties. Here, from the first and second properties, we can say the gradient is a linear function. That means the gradient satisfies the linearity property.
The applications of the gradient operator are coming soon. Haven't you subscribed yet? Please do subscribe our channel for many more lectures on various topics in mathematics. Press the bell to be notified. Thanks for watching.